Welcome to this quick guide on halohydrin formation. Today, we're looking at how alkenes transform when they react with a halogen and water. Think of it as adding an alcohol group and a halogen atom across a double bond. First, let's look at the definition on the left. A halohydrin is a functional group characterized by having a halogen, usually chlorine or bromine, in a hydroxyl group attached to adjacent carbon atoms. It essentially turns a carbon-carbon double bond into a single bond with these two specific attachments. In the center, we see the formation pathway. The reaction begins with an alkene reacting with a halogen in the presence of water. Step 1 is the formation of the halonium ion intermediate. This cyclic structure is high energy and very reactive, setting the stage for the next player to enter the scene. This is where the magic happens. Look at the energy versus time graph. While halide ions are present, water acts as a stronger nucleophile in aqueous solution. Because water is the solvent and present in large excess, it successfully intercepts the reaction. Instead of a second halogen adding to the molecule, a water molecule attacks the ring. Finally, let's look at the big picture on the right. In standard halogenation, path A, you would get a dihalide, like 1,2-dibromoethane. But when water is present, paths B and C, it outcompetes the halide ion. The result? The halohydrin becomes our major product. Let's break down the general reaction for creating a halohydrin. Looking at the reactants box on the left, we start with an alkene characterized by that carbon-carbon double bond. We react this with a halogen, which is typically chlorine or bromine, and water. In the center, you see the overall transformation. The halogen and water add across the double bond to produce our primary product, the halohydrin. A byproduct of hydrogen halide is also formed during the process. Halohydrin, it is a compound where a hydroxyl group and a halogen atom Cl or bridge are attached to adjacent carbon atoms. This specific arrangement is the hallmark of the reaction. For this to work effectively, water must be used as the solvent in large excess. Because water is everywhere in the solution, it successfully outcompetes the halogen ions to intercept the reaction and add the O group to the carbon chain. Let's see step-by-step mechanism. Step 1. Formation of the cyclic halonium ion. In the first step, the alkene's pi bond acts as a nucleophile and attacks a halogen molecule. As the halide ion is kicked out, a three-membered ring called a cyclic halonium ion is formed. As noted in the keynote, this bridged intermediate is incredibly important because it locks the stereochemistry of the molecule, preventing any bond rotation. Step 2. Nucleophilic attack by water. Next, we have the nucleophilic attack. While the halide ion we just created could attack the ring, water is our solvent. Because water is present in much higher concentrations, it wins the race and intercepts the reaction. It attacks one of the carbons from the backside, opposite to the halogen bridge. This leads to anti-addition. Step 3. Deprotonation. The final stage is deprotonation. A second water molecule arrives to pick up the extra proton from the newly attached oxygen. This acid-base step neutralizes the molecule, leaving us with our final product, a neutral halohydrin. Look at the center of the image. After the cyclic halonium ion forms, water must decide where to attack. You'll see two paths, the favored path and the disfavored path. In the favored path, the water molecule attacks the more substituted carbon. This leads to the Markovnikov-like product, which is our major regioisomer. But why does water prefer the more crowded carbon? Even though we have a rigid ring, the electronic distribution isn't equal. As shown in the bottom left callout, the bond to the more substituted carbon is actually weaker. This carbon carries a higher partial positive charge delta plus. Because it acts like a more stable, carbocation-like center, the nucleophilic water is naturally attracted to it, even if it seems more hindered. Let's look at why this happens. As we see on the left, the reaction begins by forming a locked cyclic halonium ion. Because this halogen atom forms a bridge across the top of the carbons, it creates a locked conformation. This rigid bridge physically blocks one face of the molecule, preventing any bond rotation and forcing the next step to happen in a very specific way. Backside attack by water. Next comes the backside attack. Since the halogen bridge is blocking the front face, the water molecule is forced to attack from the opposite side, or the backside. This is why we call it anti-addition. As shown in the mechanistic basis diagram, a front-side attack is completely blocked, making a trans-arrangement the only possible outcome. Product chirality and enantiomers. In the center, you can see how this affects the final product's chirality. Because the groups add to opposite faces, they end up in a trans-anti relationship. Depending on which carbon the water attacks, you often end up with a pair of enantiomers mirror images that are both anti in their configuration. Let's put theory into practice with a concrete example. We're going to look at the reaction between propene, bromine, and water to see how regiochemistry and stereochemistry play out in a real molecule. Our starting materials are propene, bridge 2, and water. In the first step, the bromine adds across the double bond to form a cyclic bromonium ion. This three-membered ring bridge is the key. It blocks one face of the molecule, setting the stage for everything that follows. Now, water enters as the nucleophile. Notice the attack happens at C2, the more substituted middle carbon. Why? Because that carbon can better handle the partial positive charge delta plus that develops as the ring begins to open. This is a crucial, Markov-Nikov-like, decision that determines our major regioisomer. After a final deprotonation step, we reach our product, 1-bromo-2-propanol. The hydroxyl group is on the second carbon, and the bromine is on the first. Notice the 3D model. The O and bromine are trans to each other, a direct result of the water attacking from the backside of the bromine bridge. Be careful, a very common mistake is putting the bromine on the middle carbon. Always remember, the nucleophile that is water wants the spot that is more stable, which is the more substituted carbon C2. Don't let the name, halogenation, trick you in halohydrin formation. The oxygen gets the better spot. If you found this helpful, hit that like button and subscribe for more pharmacy and chemistry tutorials. See you in the next video. Happy learning chemistry with Harshada.